Our topic today is future energy provisions enabled via nanotechnology. Before moving on to the session, I would like to introduce our panel. Mr. Vidya Amarapal with us today. He is the former chairman of Ceylon Electricity Board. The moderator of the webinar is the former Minister, Engineer Patali Champika Ranawaka. He is an electrical engineer and the product of University of Morocco. The resource person today is Professor Ravi Silva from the University of Surrey. He is a strong engineering professional with the Doctor of Philosophy in Electrical and Electronics Engineering from University of Cambridge. He is the Director of Advanced Technology Institute and Head of Nano Electronics Center of University of Surrey. Professor Ravi is the world expert in nanotechnology. I think the time allotted for this webinar is not enough to describe his academic and research experience, skills, publications, as well as awards he has received. So invite you to refer Google and LinkedIn for more information about him. Again, warmly welcome all of you, as well as our panel, and invite Mr. Vidya Amarapal to continue. Thank you.
Thank you, Surat. I hope I'm loud and clear.
Yes.
Greetings from United Kingdom, and good afternoon, good evening to those who are joining us from Sri Lanka, and good morning to those who are joining us from the US, and a good day anyway. It's actually customary to introduce a couple of most distinguished personalities, sons of Lanka. I would like to take the honor of introducing Professor Ravi Silva, who is going to be the key speaker this afternoon from UK. He's also a product of a free education from Sri Lanka, and his early education he received from the D.S. Senanayaka Vidyalaya, Colombo. And as Surat said, we can talk for hours and hours and days of the achievements of these two individuals. And let me very briefly introduce Professor Ravi Silva, who is a very distinguished personality here in UK, distinguished professor and the director of Advanced Technology Institute of University of Surrey. He joined the Surrey in 1995 after completing undergraduate and postgraduate degree at Cambridge University. His research interests include nanotechnology, large area electronics, and renewables, and has resulted in over 620 presentations and over 580 journal papers, has over 20,000 citations with H index of 72, and won research funding in excess of 40 million British pounds. He's the inventor of 35 patents, including key patents on low temperature growth of carbon nanotube, fabrication of high performance large area of X-ray detectors, and fabrication of large area nanotube organic solar cells, etc., etc. And most importantly, he has been recognized by Her Majesty, the Queen, as the Commander of Order of the British Empire in 2021 in Queen's New Year Honours List. Congratulations for that. And those who are not familiar with what is OBE, is the Most Excellent Order of the British Empire, which is just below the knighthood. And I hope, Professor Ravi Silva, that soon we will be able to call you sir, no sooner you get your knighthood. And with that, I would like to shift your attention to the other personality, that I would like to very briefly introduce, and he is no stranger to most of us, Honorable Patali Champika Ranawaka. And I would like to just say a few words why he's very, very appropriately fitting in to be the moderator this afternoon. Of course, he's a product of free education of Sri Lanka, and he received his BSc engineering degree from Moratuwa University, specialized in the area of power systems. And he has been one of the most prominent politicians, ministers who has contributed quite a bit to the science and technology industry. And he has been heading the ministries, if I'm to take, say, from 2000, beg your pardon, right, from 2010 to 2013, he has been heading the Ministry of Technology and Research. Interesting section is in his profile is this: deeply involved in technology development and develop knowledge-based economy. Based on this, the Minister Champika Ranawaka then developed the government investment plan for science and technology. And some of the achievements in nanotechnology for Sri Lanka, before Professor Ravi Silva commenced his speech, I would like to recollect some of these important achievements. If I may say, dry fit fabric developed for mass holdings, finally later went on to fabricate or stitch the Sri Lanka cricket t-shirt and training garment with that, and that was based on the lotus leaf, again nanotechnology invention. And optimization of fertilizer application by nanotechnology. At that, I was told that the utilization of 50% of regular requirement of fertilizer was reduced. So then graphene development project, titanium oxide project, etc., etc. Let me mention some things specially have brought in from the previous leadership that he had in Ministry of Research and Technology. The government investment plan was quite well utilized in developing the Tech City program and the plan later in the previous government. Of course, we were able to get the much needed help from the Korean government to develop the Tech City overall plan and implementation program. With that, I would like to invite Professor Ravi Silva to take the floor, and over to Ravi. Thank you.
Thank you very much, Vidya, for that wonderful introduction. I'm absolutely honored to be here and talk to you and under the auspices of the 43rd Brigade and Surat's chairmanship. I'm hugely honored to have Foreign Minister Champika Ranawaka moderating this. As I know, he's extremely busy and also has managed to find the time in being able to participate in this. Could I ask the host base to allow me to share my screen, please? Excellent. Thank you very much. So I'm deeply honored to have former Minister Champika Ranawaka chairing this session. And in particular, I have tailored my talk towards energy simply because it is so important in our lives. Now, as introduced by Vidya, nanotechnology can be used in all forms of everyday activity that include some of the clothing industries that were talked about, includes the semiconductor industry, includes the lighting technologies. Industry 4.0 is based on all sensors and AI that is controlled effectively by the inputs coming from nanotechnology. Now, all of these are important, but what I want to highlight in this particular talk is the importance to energy. And this is even more critical from a country such as ours that spends so much of our resource in this area. And I hope that many of the engineers and scientists who are involved in listening to this talk will be empowered to contribute to the activities of the country going forward. I would also like to have a subtext to my talk, which is building stronger and smarter post-COVID, simply because to acknowledge the fact that we are all living in very difficult times, strange times. It also means all of us have to make some sacrifices in our lifestyle. But what I hope is that by using the provisions enabled to us through technology and science, we can build stronger. Before I go into my talk, I'd like to thank the members of my group in particular, and James, Imaka, Shashini, Hashini, Ravi, and Kea for some of the slides that I will be using within my presentation. A brief introduction to where I come from and the work that I'll be presenting and how I've got to this point. The building that you see in the background here in blue is the Advanced Technology Institute at the University of Surrey. And we've got about 150 researchers working on different forms of advanced technologies and embedding nanotechnology within their activities. Some of these range from water filters, for which we have got a national award, Queen's Anniversary Award in some of the activities. I'm part of the electronic engineering department where we design and fabricate satellites. So we are one of the few universities in the world to make satellites all the way from cradle to grave, really, in terms of not just building satellites component by component, but also removing debris in space. So once more, if people are interested, you can see Remove Debris program that we started with ESA that shows how we can remove these particulates and satellites from space. The work within my institute was recognized by the Majesty the Queen some time back in getting a Queen's Anniversary Award. And the image that you see at the bottom left hand is from the Winter Olympics, the last Winter Olympics. And the reason I put that image up is that that's the Hyundai Pavilion at the Winter Olympics in South Korea. What is significant about this is this was highlighted as the darkest building on Earth. Now, what is important about that is that this dark color that you see is all based on carbon nanotubes. Those carbon nanotubes came from our lab. It's a spin-out company called Surrey Nanosystems. And what it emphasizes is, in the case of nanotechnology, you're dealing with particulates that are on the micron and nanoscale. But it can have impact on materials, systems, buildings that are much larger. So the importance of nanotechnology here really is on the design aspects. And by designing properly, you will be able to have those effects on much larger areas. And although the Hyundai Pavilion that was put up was associated with a showcase, so that even in the dark nights at the Winter Olympics, it stood out as a building, it has implications associated with some of the motor vehicle parts that are coming out of the car industry at present. It's used in satellites for imaging because it has the most absorptive properties available to mankind. Now, I'd like to take you back 18 months or 20 months and just put a context to my talk. Just imagine Piccadilly Circus in London, one of the most vibrant cities, one of the cities with the largest population, ethnic diversity, enjoying the day. Overnight, this Piccadilly Circus ended up looking like this. Heathrow, one of the busiest airports, or one of the 3 busiest airports in the world, moved from this particular situation to this. And places of learning, such as Cambridge, ended up having quadrangles that had no one there. King's Parade, no one there. Now, this is the impact of COVID within the UK. And I'm sure in Sri Lanka and the rest of the world, we've all seen this impact. We all have an obligation to work together to get out of this impact. And the reason why this is important is this is not just related to one aspect, but many aspects. The grim reality is that many of these aspects that have come with this sort of impact started with the use of fossil fuels. And with the use of fossil fuels, although it's something that has been absolutely paramount and significant to development, it meant that the temperature that was stable over 10,000 years suddenly became unstable. So within the geology terms, you talk about periods, epochs in time. And this is the Holocene period where there was no variation in the temperature beyond the plus or minus 0.4 degrees. The insatiable appetite for energy and quality of life and development has ended up creating islands of plastic waste. And these clearly are important in certain aspects, but we've seen why we need to get rid of this simply because we cannot continue to pollute the world in the name of development and enjoy the benefits while somewhere else your problems start piling up. And we really have made a significant change when we look at the history of mankind and say in 2.5 billion years, we are the first race that has managed to change the course of the world, because we've created what we call the Anthropocene age that has come after the Holocene age, where now, if we were to dig a hole to this current time, you will see more man-made objects, more Anthropocene type objects than natural objects. So we really have made our mark here, and probably made our mark in the wrong way. Now, clearly there have been very positive things with the unparalleled growth of quality of life and wealth creation, but maybe in a sense there is some sort of payback now coming, because the earth needs to have sustainability contained within its own activities. There are also sometimes pauses that you can have in terms of what you see and think maybe the current COVID crisis is a time to rethink our strategy going forward. And this is basically showing what happened in satellite imagery of gases coming out of China between January and February 2020. And what you immediately see is a huge drop in NOx or greenhouse gases in comparison from one month to the other, indicating maybe it is showing us a way that we need to slow down in certain areas if we want to keep our planet clean. So the post-world COVID that we need to think about going forward, and particularly with engineers and professionals there to build it, is going to be different. We need to rethink what our priorities are going to be. We need to be able to understand and engineer things going forward. The whole idea of megacities, the whole idea of developed technology that is working closely with buildings, with your transportation sector, with recreation, etc., are working together in a cohesive manner in such a way there is connectivity and information exchange. We need to start thinking of smarter ways of doing things. We need to start using supply chains. And one of the great things about nanotechnology is that you can make more efficient products with less material, more robust products, but reduce the cost and reduce the waste associated with it. All of this can come with Industry 4.0. So new innovation can come in the post-COVID world. And if we do not actually change our ways, there is a stark warning here given by the Chancellor of the Bank of England. The former Chancellor of the Bank of England, Mark Carney, indicated that the climate crisis would create significantly more deaths than the current COVID crisis we are facing. So it's a wake-up call to all of us that we have taken the earth for granted, and now we need to start thinking about ways in which to build back smarter, a better world using science and technology. Now, moving on to the main theme of my talk, which is about energy. If we start looking at the energy mix currently being used, and typically the US energy mix is very much mirrors the world energy mix when it comes to round figures. And if we look at where the energy mix was 10 years ago, typically 80% of your energy came from coal, oil, and gas, so fossil fuels. Renewable energy accounted for around 10%, nuclear about 10%. And this was at the time when Barack Obama was the president of the United States, and he had signed up to COP21, the Paris Agreement, in order to reduce greenhouse gases, etc. If we look at what happened roughly 8 years afterwards, the United States is still using nearly 80% of fossil fuels, roughly 10% of renewable energy, and 10% of nuclear. Things have not changed hugely, despite us knowing there is a huge climate crisis looming up. If we were to look at the world energy balance, again, this is an editorial that I've just written a couple of months ago to the magazine Energy and Environmental Materials. Fossil fuels make up nearly 80% of all of the world energy use currently. From a world point of view, nuclear accounts for about 5%, and renewable sources account for about 15%, with solar and wind amounting to just under 2%. So that's a world energy balance. The problem we have here is that despite knowing there are climate change obligations that we have since Kyoto in '97, we still have 80% of all our energy coming from fossil fuels alone. Now, is this sustainable? If we look at the last complete year that was not affected by COVID, and we look at the CO2 emissions, in 2018, 37.1 billion tons of CO2 was emitted globally. And as you can see in the graph on the left-hand side here, is that the total emissions in the world keeps going up. You can see that the main culprits associated are the US, the EU, and China, and India, with the rest contributing what is shown here. But we cannot continue to increase the CO2 emissions at present and leave it for the world to be a sustainable place. If we look at the correlation of the CO2 emission that you see here in blue and the temperature rise that you see in red, what you see is this correlation that beyond the 320 parts per million of CO2, there has been a relative rise that is proportional effectively between the temperature and CO2 levels. Now, one would say maybe that's associated with the data set I've used, but this data set can go up to many hundreds and thousands of years, and it will have the same sort of position. We also know at the present time, the increase in temperature is at around 1.2%, 1.2 degrees. And we cannot afford to allow this temperature to go beyond the 1.5 because there will be catastrophic effects coming into play. And these could be anything from your storms, from global warming issues with the melting of the Arctic. You could have snowstorms coming in Mexico, and these sort of weather events that are completely out of the ordinary. In fact, I will show a clip of some of those weather events when I come to that and discuss that point. Now, the solution that has been proposed is that we need to go to a net zero position. What I mean by net zero is that we need to be able to balance out the anthropogenic greenhouse gas emissions with the anthropogenic removals. Typically at the present time, there is about 20 gigatons of anthropogenic removals coming through forests, bogs, marshlands, etc. But our emissions are at around 37 gigatons. So we need to drop this from 37 all the way down to about 15 to 17 in order to have a balanced activity. And if we can keep that balanced activity, that means that we will have a net carbon emission position. If we cannot do this science-based reduction in the CO2 emissions that is now being proposed through IPCC, the problems are quite severe. So for example, if we miss our 1.5 degrees by 2050 to say 2 degrees, the predictions at present are that there will be over 11 million people exposed to extreme heat, 60 million people or more exposed to drought, 10 million more people exposed to rising sea levels. And these are just a few of the potential crises that are going to hit humankind as a result of global change, climate change. And these temperature rises will have catastrophic effects associated with flooding, precipitation, desertification, acid rain, biodiversity loss, etc. Now, this sort of movement of people and changes in climate certainly give rise to major events, extreme events, and in some cases, the spread of diseases like that we are seeing at present. If we were to look at the impact of climate change,
it's the general scientific consensus that climate change is causing an increase in extreme weather events around the world. Oh my God. From sea level rises to droughts, extreme weather can seriously cripple affected communities. But what is considered an extreme weather event? Extreme weather can be very dramatic, with fire tornadoes, wildfires, severe tropical storms, hurricanes, and cyclones being the prime examples. According to the Intergovernmental Panel on Climate Change, an extreme weather event is an occurrence that is more severe than the historical norm. They point out that even statistically, non-extreme weather events can cause significant damage to economies, societies, ecosystems, and infrastructure. As of 2012, there have been more than 800 major extreme weather events recorded worldwide, causing hundreds of billions of dollars in damage. Other sources, like the UK Met Office, show a marked increase in extreme events, which caused loss from just over 200 in 1980 to over 700 in 2015.
So what is very important to note here is that within the first 9 months, within the US, there have been more extreme events than the whole decade. Worldwide, there have been more extreme events this year than the last 10 years. So these events are happening more and more frequently. And much of this could be associated directly to the CO2 emission that is creating the increase in temperature. Now, the question to ask is there a solution to this problem? Now, looking at it holistically, we can ask also, what sustains life on Earth? If we look at the fundamental question as to what sustains life on Earth, it is energy, and it's energy from the sun. The sun not only gives us the abilities to grow our crops and to be able to farm, but it also, in the past, through fossilization of vegetation, etc., given rise to coal, petroleum, and gas. The problem we currently have is that when we use fossil fuels, you have removed a densification of carbon capture that has happened over millions of years and released all of that in one go to the atmosphere. So if we want to have a sustainable lifestyle, we need to rethink of how we do things. And we can continue to farm, we can continue to grow things, but we need to start looking at ways in which to directly use the energy that is given by the sun to the earth. Now, one could say, is this feasible? Is this possible within the current economic envelopes that we all find ourselves working in? Furthermore, if we can start using direct conversion of solar energy to electricity, it actually allows us to tackle a number of major problems. If we look at the typical energy mix associated with the users of energy from a national context or a world context, about a third of your energy is typically used for household use, domestic use. About a third of it is used for industrial use, and about a third of it is used in the transportation sector. We know that from a household point of view, in most cases, the electricity can certainly supply the energy needs there. At the moment within the UK, one of the major areas of change is the gas boiler, as to whether the gas boiler can be removed and replaced with ground source heating and electrical fans to move the air around. In the case of industry, there's no question, electricity can be the main form of energy. And in the transportation sector, as you have seen, many countries have now declared that beyond 2030 and 2035, there will not be only petrol or only diesel cars, but there will be hybrid vehicles and in particular electric vehicles coming in. So electricity really is one of the most flexible forms of energy. And the question is, if you can convert that energy from the sun through windmills or solar farms into electricity, that would certainly be helpful. Now, if you look at the amount of energy that is coming from the sun and do a very simple back of the envelope calculation to see whether the potential is there for there to be enough energy to be captured, what we find is very surprising. If you use Planck's blackbody radiation law, you can show that the total energy flux coming in is something called the Stefan Boltzmann's constant times T to the 4. And that total amount of energy that comes from the sun to the earth is around 175,000 terawatts of energy. Now, the world as a total at present uses around 15 terawatts of energy. And this world energy use is not just electricity, it's total energy use that includes the transportation, includes domestic and industry. So what is immediately apparent here is that the sun delivers to the earth over 10,000 times more energy than we use. So maybe as an engineer, something that one could think is, isn't it time we try to use even a fraction of this energy and power things? If we were to look at it graphically, the big yellow box is the total amount of energy that irradiates the earth from the sun. These various boxes inside contain the total capacity of wind in purple, biogas, biomass in green, and geothermal. And this orange box in front is basically the total energy expected to be used by 2050. So it represents 50 terawatts of energy. So what this is basically saying is, from a potential and capacity point of view, there is certainly enough energy that hits the earth that can be utilized. In terms of the economic equation, what I show here is the comparison of the different renewable energies that are most popular with the different fossil fuel energies. So what you see in this light green band are the fossil fuel cost range. So the cost range for fossil fuels from a worldwide perspective is between 5 cents per kilowatt hour to around 17 cents per kilowatt hour. That would equate to about $50 per megawatt hour to $170 per megawatt. What we see within these graphs is, within the last 10 years, the onshore wind price has kept coming down and down and down to the point where it's now pretty much close to the lowest cost you would pay for fossil fuel. Solar energy, once more, solar PV, started high 10 years ago. It's come crashing down to the point now, and in this case it's 2019, and I'll show you the current data in the next slide. It's comparable to the lowest cost. So no longer can we say there is a cost argument that fossil fuels should be retained. And that's something I'm very happy to take a challenge on, and we can go back and look at those numbers from a worldwide scale, whether that's correct or not. Now, this was what I did in this editorial that I wrote for Energy and Environmental Materials, where I plotted out in the last 10 years, what is the average cost people have paid for energy. If I take nuclear energy, that's shown in blue here, that's at around 170, 180 per megawatt hour. If I take coal, that's probably around 120. If I take a combined gas systems, we're talking about 40. If I take wind and solar, it's coming below 30 at present. And this is not the end of these, because the predictions at the moment show that there may be some plateauing, but I don't believe that is the case, as I'll show you in the analysis that follows. In my view, I believe that the energy cost associated with solar will probably drop to less than $10 per megawatt hour. In fact, last month, a power purchase agreement in Saudi Arabia sold it at 1 cent per kilowatt hour. And that's for over 200 megawatts of energy. If we say hydrogen is the future, if I can use energy, electricity from my solar system to run an electrolyzer, I can now produce a kilogram of hydrogen at 1.6 US dollars per kilogram. And once more, hydrogen, which was thought to be too expensive really to power networks, despite giving very clean energy, becomes feasible. So this is all possible with silicon. This is all possible by looking at silicon in absorbing more of the energy, in capturing more of the energy, using what you call the PERC cell in order to design the back nanoscale structure for maximum efficiency associated with being able to absorb all of the energy that hits your solar cell. If we look at the last complete year that was not COVID affected with new energy deployments, 55% of new energy deployments worldwide was associated with solar PV, 32% with onshore wind, 10% with offshore wind. So what this shows is that the world is moving towards these renewable energies, not because someone says they should do it. It's simply an economic argument now. And you need to have free economy in order to allow these to happen, simply because even in terms of volume, what you see is that the larger the volume, the lower the price gets. As a result of the work that we are doing on solar energy, we also did some work to show the government of business, energy and industrial strategy in the UK what the cost reductions are. And for the first time last year, BEIS accepted and acknowledged the fact that large-scale solar and onshore wind is the cheapest form of energy. So although there is Hinkley Point C, which is set to buy electricity based on nuclear at £92 per megawatt hour, solar at present can deliver that at less than 30. So as a result, there is a major shift in thinking and planning going forward, but that will have to be accompanied by being able to have novel storage solutions in order to store your energy, as well as having smart grids and moving away from a single grid connected system to a much more smarter, localized grid distribution in local areas. We've also shown some of the learning curves associated with solar cost and done some training algorithms to show how the cost keeps decreasing. And all these graphs show is the levelized cost of electricity going down according to the world statistics, going down based on the installed capacity, and how there could be an apparent linear, log linear relationship between the levelized cost of electricity and the installed capacity. And this we can predict for the UK will go down to about 3 to 4 pence in the coming years. As a result of much of the work that is being done within the UK to show the impact of renewable energy into the national grid system, there have been a number of parliamentary acts and strategy documents that have been put in place. And within the last 3 to 4 years, there has been major change in policy, with the last coming out last year in the 10-point plan that gives renewable energy a major boost. Furthermore, there are new interconnects being connected so that we can get hydroelectricity from Norway, so direct electricity lines to use the hydro capability in order to stop brownouts. And in terms of costing worldwide, you can see in Los Angeles, 2 cents per kilowatt hour, Portuguese government, 1.3 cents per kilowatt hour, Saudi Arabia, as I said, 1 pence per kilowatt hour, and Sao Paulo, 1.5 pence per kilowatt hour. These are all happening worldwide, and it's something that we can't afford to miss. Looking at Sri Lanka and seeing whether Sri Lanka also has that capacity to take advantage of this particular situation, one can very easily start looking at the possibility, and this is not with huge amounts of research, etc., but just a cursory look. We can start looking at the solar irradiance or insolation, and we can also look at population maps. And what you immediately notice that there is a lot of solar irradiance that we can take into account, particularly in areas where you have large populations. And this can certainly start impacting. And when I looked at things about 5 years ago, typically speaking, the country had around 50% renewables, simply because you already had 40% with hydro. And hydroelectricity is certainly a renewable form of energy. And if you add the new renewables of 11 or 12%, that comes up to your 50%, with thermal coal and thermal oil and gas making up the remainder. If you look at historically, you can see that the domestic, industrial, and commercial activities have effectively shared the different amounts of electrical use. And looking at the UNDP report that came out recently, asking and showing that Sri Lanka can reach its 50% or 100% renewable targets by 2050, it looked at the increase in energy demand per year and indicated that there will be a 6% increase associated with that. Then by simply using global irradiance data, you can map out the space that is needed if you were to look for solar cell-based electrical production. This is purely electricity as opposed to all of the other energy needs. But looking at purely the electricity requirements, what we can do is to say with 14% modular efficiency, this is using amorphous silicon and older silicon grade devices. The black line shows the amount of area that you need in order to meet the electricity demand of the country. If you use typical silicon modules at the moment, which is around 18 to 20%, it's shown in blue here. And just to put things into context, if we take the 2020 number of around 35 square kilometers, that is about half or quarter the size of the Seranayaka Samudra. So effectively, by having solar cells in an area of the size of the Seranayaka Samudra, we can satisfy all of our energy needs for electricity generation. According to the UNDP map, it showed a very rosy picture that by 2030, we would use 25% fossil, which will go down to 10% and go to 5%. So these are proposals that were put in. But you can also start looking at some of the least cost long-term generation plans that were put forward. And this is where I looked at some of the initial numbers that were coming. When I looked at initially some of these numbers in 2015, we had about 1.8 gigawatts of renewable, that's major hydro plus other renewables. And then we had a further 2 gigawatts roughly of thermal and oil and coal systems. So if I were to take roughly, that's 50% of renewables, 50% of fossil fuels. What is slightly worrying is that our energy needs keep going up. Our hydro is pretty much constant. We need to try and increase our renewable energy components if we want to try and keep your 50-50 mark, if that's the objective going forward. But ideally what you want is to move higher than 50% in terms of renewable energy. According to the 2018 plans that were put forward, the new energy mix for the next 20 years indicated again to maintain the parity of the 50-50 roughly associated with activities. But my thought process is that we can do better from a Sri Lankan perspective, and particularly based on the fact that solar energy is now getting cheaper and cheaper year on year. We should be able to try to beat those plans that were put down in 2017-18, where the target was that by 2027, we would have up to 1 gigawatt of rooftop and, 1 gigawatt of ground mounted solar and 300 megawatts of rooftop. Clearly, there are many other plans that have come more recently that I'm aware of that is looking at things. But the problem I'm seeing at present is that it's not moving with the deployment that is needed. Whereas on the other hand, India have moved forward with their Nehru challenge. Looking very simplistically as to what does it take to have up to 1 gigawatt of energy that is required from solar to add to the current 1.8 gigawatts of renewable energy. What we can do is create solar farms. And this is something I believe the government is very strongly advocating. And if we were to start overlapping the less dense areas with high insulation of solar energy, you could probably select places such as Kilinochchi, Wanakai, Nila Valley, Anuradhapura, etc., to mount roughly 100 megawatt solar farms. And by having it distributed, it allows you to be able to meet the necessary energy challenges. If you look at the peak power supply in 2016, when I looked at it, the peak power supply was about 1.6 gigawatts. By having this extra gigawatt of energy by solar or wind provided, it's possible that we can also make sure there are no brownouts in the country and work with some of the cheapest energy systems available. We already know that there are 100 megawatt plus solar and wind farms being looked at Punarin and in Monaragala. But again, I'm not sure as to how much of that activity has taken place. But what is very important to note is the space that you require to do this sort of increased solar energy activities is not as significant as most people initially considered when they said solar farms will destroy the environment, etc. In terms, if we want to think about space-wise, if we take Sri Lanka space as 65,600 square kilometers, the relative space that is needed is not hugely significant. And we certainly can find the space. And by moving from module efficiencies of 18 to 20% to 30% efficiency modules, you can certainly reduce that space requirement even further. As indicated earlier, if we take to looking at floating solar, for example, the Senanayaka Samudra has a 91 square kilometers. You could probably get 1 gigawatt of energy by using just a quarter of that area in terms of space for solar. So this is just an idea that solar can give you the energy that is required. The cost of it is lower than any other fossil fuel around, and it is not going to take up farmland or any other useful land if we were to go down that route. Furthermore, there has been a number of discussions as to the time it takes to build things. Solar and wind are probably the fastest installation and deployment that you can get in any country. In fact, in Australia, you would find Elon Musk challenge the Australian government that within 12 months, he will not just have his solar installations, but also the storage available. And he said he will pay for that if he was not going to be able to deliver. So these are the things that certainly we can look to prepare. In terms of storage, there are a number of options that can be looked at. And in my view, pumped hydro is a very important area that we need to look at. You do not need heads of 100 or 50 meters. The present technology that is available with hydroelectricity can even run efficient systems with 5 to 10 meters as long as there is flow associated with it. And I'll show you some pictures of a project that we are doing in India that emphasize the fact that you can start looking into this sort of activity. So depending on the times that we need in order to fill the potential energy gaps, we can certainly start looking at different types of energy, which needs seconds, minutes, hours, etc., in terms of the storage capacity. So these are engineering problems that there are solutions to, with the cost of storage also coming down very fast at present. I'm working currently with the Smart Cities initiative in the Gujarat and in the Vadodara area. We are looking at a 1 to 2 meter head in being able to generate electricity through flowing water that they have within their various villages within the activity. And what we are looking for is a mixed solar and wind activity, just in order to support some of the other energy infrastructure that is available within the area. I do know that Sri Lanka have many other ideas and plans that have been put forward. In some cases, there are even plans for 80% renewable that is being proposed. And this will cost a lot of money, and certainly it needs to be done with a significant design aspects associated. But from a worldwide point of view, again, looking at it globally, if we want to power the whole of the world with solar, what you see here in these green boxes with a red outline is the total area that I need with 20% efficient solar cells to power the world. So whether we like it or not, the rest of the world will move towards solar and wind as the two main intermittent sources of energy, renewable energy required. In order to be able to balance out the summer and the winter months, there will have to be different forms of storage that comes in, and that storage will certainly become cheaper as we go along. Now, what about the next generation? So I indicated that silicon at the present has got PERC cells that have been improved to a huge degree by nanoscale structuring on the surfaces, anti-reflection coatings, etc. We are also looking to see what could happen beyond that. And in terms of looking beyond that, what we are looking at is the next generation of solar paints. So the idea here is that within your active paint, you would have nanoparticles in there. Those nanoparticles will ensure that the total light that falls in that area will be absorbed. To put things into context, if this is my silicon wafer, the green block here, the thickness of my silicon wafer is typically 300 microns. I can get the same absorptivity associated with the silicon with 100 nanometers of organic, inorganic mixtures. So immediately I have reduced 1,000-fold the material I'm using. The silicon was 300 microns. The organic, inorganic mix here is 100 nanometers. The organic, inorganic mix that we have will be in the form of solutions, and each of those layers will have different properties. One for electrical transport, one for active absorption, another for hole transport, and the final one for electrical conductivity. Using this process, we are working with Europe on a number of projects. We started off on a project called Smartronics that not just looked at these solar cells, but also built large area roll-to-roll manufacturing systems in order to make solar cells on organics. And now we are going in creating an open market within Europe in Cornet and another newest grant that we got called Music Code to be able to produce this in large quantities. So at present, these cells can be bought for select customers, but it's still not mainstream. Within the next 2 years, it's highly likely these cells will come mainstream. And with the work that is happening most recently in materials such as perovskites, we can push the solar cell efficiency on materials such as silicon up to 30% by having what you call tandem solar cells. And those tandem solar cells are going to be so much more cheaper in terms of manufacture and efficiency, that not only get reduced in cost because of the new techniques and materials being used, but also the bulk manufacturing that will drop the cost associated with it. So let me end this talk by emphasizing what I've tried to do is to show the importance of using science and technology, in particular nanoscale structuring, in order to solve some of the biggest problems we have, and energy is probably the largest problem. Energy security to a country can give it huge benefits, and that is something that we need to all try to do in order to get that for Sri Lanka. Sustainability needs to be done so that we do not change our planet and use the needs of future generations. The UN development goals, within its 17 goals, encompasses these sort of developments that need to take place. And from a Sri Lankan point of view, I'm very, very determined that we make sure the heritage that we have, not just the cultural heritage, but also the environmental heritage that we have, is given to our future generations, so they can not only enjoy free water and air, but free light that gives them the energy, so that we can call free energy also being part and parcel of that mix. So with that, I conclude to say that the sun is the source of nearly all forms of energy that is currently being used. It really does allow us to have a higher quality of life, and there's a direct correlation between energy use per capita and quality of life. At present, 80% of the world energy comes from fossil fuels. Unfortunately, the CO2 and greenhouse gases poison the climate that we have. We need to reduce that. We need to move towards a net carbon zero activity. And I want us, as in Sri Lanka, to consider light as part of our heritage, so that we can have solar energy, hopefully for free, beyond 2035 moving forward. So with that, I thank you very much for your attention and look forward to answering any questions that you may have. Thank you very much.
Thank you, Professor Ravi Silva, for that very inspiring presentation and insight to the energy with the use of nanotechnology. And let me hand over the audience, or the floor, to Colombo now, to the moderator to take up the Q&A. There are some questions on the Q&A and also on chat. I would appreciate if that can be addressed before verbal Q&A. Thank you.
Thank you, Vidya. Now the floor is yours. Thank you, Professor, for your inspiring talk and presentation. As you know, now the New York subway is now submerged with the huge torrential rains experiencing there in New York. A few weeks ago, Germany, China, all these countries experienced the bad consequences of climate change. And the solution, new energy sources and renewable energy sources. And the main problem of these intermittent energy sources like wind and solar is now solved by nanotechnology using very efficient solar cells plus kind of a storage facility. Thank you very much again. And I think most of you have few questions. Now, feel free to ask questions from Professor Ravi Silva via this app, and please concern about the time limit we have. Now use the floor.
Before that, Professor, may I interrupt you? There are some questions posted in the Q&A. If you can just click them and address those, and then we can go to Prasanna, who has raised a hand.
Certainly, I can do that. Very happy to do so. So I think Janaka Vijayasuriya asks, are these predictions for solar energy still valid when going for mass scale production of energy? I do believe they are still valid, Janaka. In fact, I think the cost will keep coming down even further. So therefore, hopefully we will continue with that. And what is very important to note is at the present, it's only silicon that is dominating. 90% of the world's solar cells is still made out of silicon. Soon as these other plastic materials come through, you will have competition for silicon to drop their price even further. So I certainly believe that is valid. In terms of the economic, social, environmental and political impacts, the rapid increase of silicon processing, that's a very good comment that you make there. We need to think of recycling there. So you're absolutely right. We need processors and being able to recycle things appropriately. So much like steel recycling came about, we can do that. Sharjah has asked a question about recycling of solar panels. How much are we prepared for this challenge? Very good point there, Sharjah. And that is exactly what we need to do to move forward. I know there are a number of programs currently being pushed forward within India to look into this particular problem because of the Nehru program for getting 100 gigawatts of energy. Abdul Kadir asks, is there a difference between the rays we receive from the sun country to country? Absolutely. Sri Lanka is absolutely blessed being close to the equator so that we have some of the largest number of sunlight hours. So as a result, if countries such as Germany and the UK are looking at a solar future, Sri Lanka can get 150% of the light that is coming into Germany and the West. So therefore, we certainly should be looking into it. Kandipan asks about the presentation that will be available later. In terms of solar cell efficiency, Abdul Kadir asks, are they different country to country? No, the panel efficiencies will be the same, but what you have insulation wise will be different. That's basically the amount of radiation that is going to hit your solar panel. So we need to correct for it. And that can be done quite easily. Hansa Prasad asks, is there a way to use nanotechnology for wind power generation? Yes, there are some areas in which this is being looked at, and in particular in the blade technology that is being used. So some of the blades, most of the blades are based out of CFRP, carbon fiber reinforced polymers, and we can make the strength of those carbon fiber reinforced polymers significantly higher. But more importantly, you can make the aerodynamics in such a way that you can get your blades to spin faster by having the right aerodynamics associated with it. Nuan Sinhalage asked for a copy of the presentation. Very happy to do so. Kandipan, details on nanotechnology in paints. This is something that is currently happening, and it is a lot of countries have this because this will be a technology of the future. So for example, the US, Japan, China, etc. have done many of these projects, and it's being kept as trade secrets and patents. Saminda Abevikrama talks about using of graphene. Graphene is going to be absolutely central for any sort of battery storage unit. If you take lithium ion or any of those, you need to have the lithium ions being stored in one of the electrodes, and graphene would be that preferred choice. So certainly the vein graphite you can get in Sri Lanka is perfectly placed in order to compete with the best in the world. Jayamangala Jayasuriya Vijay Surya asks, we operate mostly in urban and high consumer density areas, distributing electricity. What about the overhead lines, etc.? This is something that the CEB have great expertise in, and I wouldn't want to try and tell them how to do their job, but they have huge experience in how to do the necessary distribution. But I think what needs to be done is a new infrastructure of smart grids associated with regional activities rather than having a single main grid that is providing things. And that's something that we can certainly look forward to. Hansa Prasad asked about the balance of power systems with solar power generation is higher. This is something that we always have to keep in mind, and particularly being able to ensure that you have an energy mix associated with it. And that's why Sri Lanka is also blessed, because it has a lot of wind energy. So between wind and solar with pumped hydro, it has got probably the perfect mixture of green energy sources we can use. So it's something that we need to push UN and other government organizations, international organizations to help us. I think many of the other discussion points here is on solar panels and nanotechnology to improve things. And these are activities that certainly we will be doing, and we will continue to do so. So maybe I can pass on to the moderator now.
Thank you very much, Professor. Anyone can now raise your questions directly to the Professor.
Prasanna, you raised your hand. If you're there, can you unmute and ask your question directly from Professor Silva, please?
Hello, can you hear me?
Yes, please.
Professor Silva, just to get an understanding about the solar power storage, the storage devices and the future of the storage devices, the battery and the technology. Something about that, please?
Yeah, it's a very good point you make, Prasanna. I think when you have energy, if you can use it at point of use or point of production, that is very good. But when it comes to large scale, we have to start thinking about much more the whole consumer area. So we have to have the storage element. And I think that's where Sri Lanka is beautifully placed, because we can have hydropower or pumped hydro. So whenever we have too much solar energy being produced, we use that to drive our motor pumps to pump water up to our hydro stations. And then when the demand is high or the peak is there, we just use it backwards. So hydro would be my preferred choice of energy storage. And I also indicated that at the present, new technologies mean that you can have pretty good efficiencies with even 2 to 5 meters head of hydro, which means that we can basically have hydro as long as there is flowing water. In fact, Her Majesty the Queen in Windsor has got a hydropower plant behind in the castle that provides some of the power to it. So it just shows it can happen in many parts of the world and areas.
Okay, sir. Okay, thank you very much.
Any more questions from the floor?
4 participants raised hands.
I think Chamat Silva has raised his hand.
Yeah, Professor, thank you very much for your inspiring speech, actually. Professor, the question is, today the solar cells efficiency, how much and with the nanotechnology, how much can you increase the solar cells efficiency in future?
Very good point, Chamat. So again, at the moment, your silicon solar cells are probably in use going at about 20 to 22%. In labs, they're about 25%. Now, by using a perovskite layer on top, you can actually increase that to 30%. So my view is that it's probably going to be between 30 to 32% in terms of the maximum power efficiency that we will use from a solar cell point of view. And that is perfectly adequate when it comes to being able to generate the energy that we require at present. You can get solar cells that are operating at 45% efficiency, but these are very, very expensive.
Can we have the next question, please?
Professor Amrav Jayapala.
Yeah, can you hear me?
Yes, 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 Prof.
Prof. Ravi, thank you very much for the presentation. And I have 2 points to a little bit differ from your view. That is, that when we plot the cost, the levelized cost with the different technologies, we have to probably, in Sri Lankan context as an island network, we have to consider about the dispatchability also, because the thermal power plants are dispatchable, whereas the intermittent sources like solar and wind are non-dispatchable. Therefore, there's an additional cost of storage if we want to use that energy elsewhere. So which should be added up to the cost that when we compare with the dispatchable power plants and non-dispatchable power plant. That is one point that I would like to point out. And then the second point is, now we talked about this 37 billion tons of carbon emissions worldwide, and whereas the nature can absorb about 20 or less than, say, slightly below that 17 billion tons a year. But if you take a Sri Lankan context, we emit about 1 ton per person. So very low emissions here in Sri Lanka. And if the world emit at that rate, so it will be only 8 billion tons a year with the 8 billion population. So which is far below what the nature can absorb, and very much sustainability can be maintained. So a good question that you and me and we should all encourage to ask in the international forums is how fast the Europeans and Americans and Chinese and Indians, they're big emitters, how fast they can shut down their thermal power plants, especially coal power plants, at the rate of say 5% or 10% a year, so that this sustainability can be achieved. Thank you.
Thank you, Anura. I think that was beautifully presented, the questions, but I will differ on my opinion on one of them in particular. The one I would differ is the dispatchability actually has been taken into the levelized cost of electricity that I presented, and in particular to the ones that were done for the UK. But you're absolutely right. It depends entirely on the available technologies and what your base loads, etc., are going to be. But it certainly has to be part of the LCOE, otherwise you don't get a right figure. In terms of the tonnage of usage, you're absolutely right. I think we all need to do our fair share. It is very interesting point you make there, because I think in the science-based numbers to get to 1.5 degrees or carbon net zero by 2050, whether countries themselves should be corrected for that or not. Now, I believe when the science-based target, it is corrected for countries. So I think the international community have tried to do it correctly. So if, for example, a Sri Lankan company says we are using SBTI, that will be corrected. So as a result, the international community is trying to be fair. But the main point I think that we all have to learn is that we only have one Earth. We all share it. And probably the best thing on Earth is the fact that we have a common environment. And whatever we do in one country affects another country. But you're absolutely right. We have to get the countries that have polluted the world more, that have already developed their own countries first, and then talk about reducing the potential development. But even then, if the cost of renewable energy at the moment is lower than the fossil fuel cost, I can't see an argument why we shouldn't go to non-fossil fuel based systems.
Professor, may I add something to your argument?
Please do, please.
I think this 2021 is very important year. The IPCC, the main body for the climate change since they are in UN, now they have published their new outlook. I think it is very important to look this new IPCC report, which clearly stipulated the current global trends are now becoming more and more going to be very disastrous way. And now the extreme weather patterns now experienced by US, the European countries, even there in China and even here in Sri Lanka, actually would indicate the coming future is not good. The consequences are much more bitter than we thought. I think the IPCC's current report make kind of a new suggestions how to deal with this climate change events with by replacing the fossil fuels with renewable sources.
Yeah, absolutely. I can't agree more with what you said, Mr. I think we as Sri Lanka should also push to say, can we become a sort of test bed for new technologies? Because there is $100 billion fund also set up for demonstrating green technologies, the Breakthrough Fund. So I think if the government can bring some of our very, very good scientists and engineers together to come up with new technologies that we can demonstrate, it would be a huge asset for the country.
Thank you, Professor. May I seek your permission to take up two more questions? I know we have taken a huge amount of time of your busy schedule this afternoon. Can we have Chanaka to come up with his question, please?
Hello, can you hear me?
Yes.
Yes, please.
Yeah, Professor Ravi, thank you very much for your nice presentation. I have a little bit different question regarding absorbing of the solar energy. Now, solar energy, I mean, solar emission has been taken by Earth for its sustain. So if we are absorbing or if we are using portion of this energy, solar energy for our energy consumption, how it would affect the world. I mean, we've been using fossil fuels, so it has affected now in like global warming. So if we are taking some portion of energy that has been there for like millions of years for our consumption, so my question is, will there be any consequences, or what do you think?
It's a very interesting philosophical question, Chanak. I think I think you can debate about it for a long time, but possibly my view is that because we currently have a 10,000 oversupply associated with the energy that we need to run the world versus the energy that is coming from the sun, we probably will be taking a very, very small fraction. So initially, it's probably going to be less significant, but at the moment, within 1 hour, the world gets enough energy to run the world for a year. So that's the proportions we need to think about. So it is a very small fraction that we are using.
Right. Can you have Bandula? Bandula, can you come up with your question, please? Okay. We have an opportunity for one last question. If not, we will close the session. All right. Thank you very much, Professor Ravi Silva, for inspiring presentation, and I'm sure everyone will agree with me, and we will be looking forward to cooperate with you and keep in touch with you, and it'll be a source of inspiration and source of information and knowledge for Sri Lankan 43rd Brigade. As I explained to you what is 43rd Brigade is, and it is an army empowered by the people or the children who received a free education on account of taxpayers' money in Sri Lanka, and they are with a massive vision. And thank you, 43rd Brigade and organizers for facilitating the presentation of Professor Ravi Silva. And thank you, our moderator, Honorable Patali Champika Ranawaka, for taking his valuable time, your valuable time to moderate this session. And thank you for each and every participant this evening from Colombo, from various parts of the world. And one time I saw something like 170. And I'm sure it was nothing but for the inspiration speech expected delivered by Professor Ravi Silva. Thank you again, and thank you, everyone.